All right, good morning, everyone. My name is Abraham Liddell. I'm a postdoctoral research fellow here in the Data Science Institute. Today, I would like to introduce Dan Westervelt as part of our DSI Distinguished Speaker Series. Dr. Dan Westervelt is the Lamont Assistant Research Professor at Columbia University's Lamont Doherty Earth Observatory in New York. He is also an affiliate faculty member of the Columbia University Data Science Institute and an affiliated scientist with NASA Goddard Institute for Space Studies and an air pollution advisor to the U.S. State Department. He's also a Columbia University Climate and Life Fellow. His current research spans from air quality and climate modeling to deployment and calibration of low-cost sensors for air quality. Prior to his faculty position at Lamont Doherty Earth Observatory, he worked as an associate research scientist at LDEO and as a science, technology, and environmental policy postdoctoral research associate at Princeton University. He completed his PhD degree in May of 2013 in civil and environmental engineering from Carnegie Mellon University. Please welcome Professor Dan Westervelt.
All right. Thanks a lot, Abraham, for that introduction. So yeah, it's really great to be here. So I'll talk today about data science and air pollution, specifically a lot of applications in major cities in Africa. And so the work I'll introduce and discuss will span a huge range of data types, starting from something called low-cost sensors, going all the way to more fancy techniques like climate models and computer and air quality models that are run on high-performance computing clusters. So I first want to just acknowledge group members here in my group. Sorry, let me clear that. It's a little better. So these are the folks that have contributed to some of this work, some researchers and PhD students in my group. I also want to acknowledge a lot of collaborators that at different universities and different agencies in Africa. So for some of the data I'm going to show, we have been working hand in hand with universities in many countries in Africa, also with some regulatory agencies, some government agencies. And we also do a lot of training and capacity building and sort of building up and promoting the careers of the African scientists that are involved in this work. So none of this would be possible without their contribution and without the contribution of the folks here at Columbia as well. So I'm going to start with a little bit of motivation, not surprisingly. Exposure to ambient PM 2.5, which is a type of air pollutant, causes about 1.2 million premature deaths in Africa every year, and about 5 million premature deaths globally. So this is one of the leading risk factors for premature mortality out of anything. Out of all the ways that can contribute to mortality, air pollution is typically ranked at the top 5. And specifically, what is PM 2.5? Well, it's small particles. These are solid or liquid particles that are less than 2.5 micrometers in diameter. So they're kind of very small. And this figure here kind of shows the size comparison for what we're talking about. These very small, pink dots here would be relevant or compared against a human hair or a fine grain of beach sand. And then this big picture on the left is some filters taken from Nairobi, Kenya, a little over a year ago. And this is on the left, a collection of pollution on the filter after a couple of weeks. And then just for reference, a clean filter on the right. So you can see that just visually the Nairobi, and it's true for other African cities as well, there's a high level of air pollution. The other reason that we care about air pollution is because it impacts climate change. And so I just wanted to briefly talk about that as well without worrying too much about the mechanisms here. But you basically have kind of two main ways that particles, or we sometimes call them aerosols, which atmospheric aerosols just means particles suspended in a gas. And of course, in the case of atmospheric aerosols, the gas is the air in the atmosphere. So aerosols, particles kind of used interchangeably. You might see that throughout this talk. But basically, aerosols can do two things. They can directly interact with incoming solar radiation, so they can scatter sunlight. Some of them can absorb sunlight as well, but generally they can attenuate sunlight. And of course, that's going to have effects on both the surface temperature, but also things like the hydrological cycle, so rainfall. In addition to that, they can also have what are called indirect effects, which is what's here on the left. And this is more related to the fact that these small particles that exist in the atmosphere serve as seeds for clouds. So clouds form around these by water vapor condensing around these particles. And so changes in the abundance of these particles in the atmosphere via human activity or even natural activity impacts climate. So generally speaking, increasing aerosol abundance results in surface cooling. That means that as you have more aerosol, you get more scattering of that sunlight. And so it's exerting a cooling effect on the Earth. It also generally results in less precipitation, weakened rainfall. Now, I'm going to just preface that, sort of caveat that by saying it's more complex. This is a generalization depending on the type of aerosol, what's the chemical composition, what's the size of the particles, what's the shape of the particles. All of that sort of plays into the to the whether or not these are cooling or warming or drying or wetting. But when you take sort of the net effect, increasing aerosols generally results in cooler temperatures at the surface and less precipitation. And so the other flip side of that is that if you have reductions in aerosols and reductions in particles in the atmosphere, then you get the opposite. You get surface warming and enhanced precipitation. And so that's going to be important because, as we'll see later, there's a strong reason to reduce the amount of particles in the atmosphere. And that's what I just mentioned in my previous slide, because they contribute to 5 million deaths around the world every year. So one of the problems with understanding all of this is that air pollution data is very sparse globally. We just don't have a lot of data on it. In particular, this is again talking about PM 2.5. So these are the small particles that cause the biggest health impact. This is the density of PM 2.5 monitors around the world per million people. And you can see that in sort of wealthier nations like the United States, Canada, Europe, we have higher density. We have a decent amount of data. But then if you look at the global south, especially, I'm going to focus on Africa. If you look at sub-Saharan Africa, there's many countries that have absolutely no data, and the places that do have, very little data. So this is a huge blind spot in both understanding, the impacts on people's health and also from the climate perspective that I mentioned. And so there's been this exciting growth in the last, 10, 15 years about these sort of so-called low-cost devices for collecting data on air pollution. And so these are devices that are orders of magnitude cheaper. They're, if you a typical research grade sort of gold standard instrument, we typically call those reference monitors, by the way. But one of those is something around $25,000. They can be as much as $100,000. It sort of depends on, what type. The low cost sensors, on the other hand, are, around 200 or maybe even at some, at maximum, maybe like $1,000. So they're, they're orders of magnitude cheaper. And they could be an alternative, especially in resource limited areas where we don't have a lot of data and we don't have a lot of resources at the moment to, put all of these research grade reference monitors, all throughout the locations. So this is a photo here of some of the typical types. I'll talk a little bit more about them, but one of the big issues then is that the data quality is not going to be as good. All right. So if you're getting something for $200 that that really is worth, 25,000, then you should probably expect the data quality to be not quite as good. And so there's some work that needs to be done there to improve that and to sort of calibrate and correct those low cost sensors. And so that's what I'll talk a little bit about here. These are just some of the types of devices that are commonly available on the market. So the one on the upper left here is called a PurpleAir. This is probably one of the most famous devices of these. If you go to purpleair.com, you can see their map there, all over the United States, all over Europe, all over the world, really, but still limited in places like sub-Saharan Africa. But they're very simple. Their data is freely reported online. I've put a couple of others here as well that are sort of common. Each of these devices that I have up here, this is a Clarity node, for example. It's got the solar panel and sort of a cellular data transmitter. They essentially all kind of work the same way. They may have different sort of peripheral features, like this one has a solar panel, for example. This one doesn't. This one needs wall power. But as for how they detect PM 2.5 air pollution, they all basically do the same thing, and they all even have the same little chamber that measures the PM 2.5, and it's what's pictured here at the bottom. It's called a Plantower PM 2.5 optical monitor. So that's a photo of it, and you can even see it here in the guts. There's two of them in the PurpleAir, and then this is sort of a schematic of how it works. So there's basically a fan, and the fan draws in the air, comes through the chamber. There's a laser sort of in the red wavelength, around 500 nanometers or so, and then there's a photodetector on the other end. And what actually gets measured is the scattering, mostly just scattering of the particles. So how much light is not reaching that photodetector is then translated into concentrations, mass per volume of pollution. So it's an indirect measurement. This is another schematic of what I was just talking about. You've got your light source here on the right. You've got your photodiode. There's probably like a lens to focus it. When there's no aerosol or no particles in the chamber, you'll have kind of a constant photodiode signal. When there's particles that are attenuating that light, then you'll get sort of these dips in the photodiode signal. And then that can be sort of converted to particulate matter mass. It requires assumptions about the physics of aerosols. It requires assumptions about their size, because all particles don't come at the same size. There's a distribution of them. So it requires some assumptions about that. It requires some assumptions about their density. Particles, depending on what kind of composition they have, might have different densities. So it's definitely not perfect. There's a lot of assumptions that go in, but I'll try to show you throughout this talk that we can actually get pretty good data out of them. So speaking about what can cause these things to fail, not really fail, but just to not produce very accurate data. There's a few shown in this schematic here. I'm going to draw your attention to the one on the far right, where my laser pointer is right now. So in this case, we have a similar figure to what I was showing. And we have a small particle that has been coated with water. That's what this blue is supposed to be. So particles kind of naturally take up water, depending on what the ambient humidity is, they'll take up water. That is going to not be able to be understood by this optical device. And so if you have, if we go to the second panel from the left here, if you have a particle that is more massive, this is bigger right here, it gives us this sort of photodiode signal. And then we take, if we go to the far right panel, we take a smaller particle, but one that has some water coating it. That's going to actually give you the same reading basically as that more massive particle. But in reality, you're looking at a smaller or a less massive particle. And so this is why that the most expensive types of monitors for air quality typically have dryers. They dry out the air so that there's not a lot of humidity able to condense around the particles. So, oh, okay, yeah.
Is it okay to ask Dory, or should I wait?
Up to the host, I guess. Yeah, it's fine with me. Yeah, okay.
I'm learning about 2.5. The composition, what's the actual particle made from? Does that even matter to the harm that it can cause?
Yeah, it does. Yeah, for sure. I mean, there's a huge variety of compositions. You have like a lot of inorganic chemicals. You have a lot of like sulfates. There's also a host of, maybe thousands of different organic types, the carbon, hydrogen. There's things like metals, there's iron and mercury and things like that are typically more toxic to people's health. So those, if the particles contain that, then it's definitely different than if it's just a particle that contains sulfate, which is not necessarily as harmful. So yeah, the composition matters a lot. I think there's been a lot of ongoing studies of like, which types of compositions matter the most for health effects. But right now, we don't have enough information on that. And so all of the health studies and all of the guidelines, the regulatory guidelines, are based on the total particle mass. Yep. Okay. So given these limitations with low-cost sensors, there needs to be some work done to correct them. And this is traditionally done by simply taking some low-cost sensors and putting them side by side with one of the more expensive, research grade, gold standard instruments, and just let them sample the same air for a long period of time. And you have this side by side data set. So this is a picture on the left of us doing that at Lamont. The big thing here with like the tall tower is the reference monitors. This directly measures the particle mass in a more robust way. And then on the sides here, we have some low-cost sensors that are just sort of sampling the same air. This is done out at Lamont. So for those that aren't familiar, the Lamont campus is up here in Palisades, New York, relative to where we are here. But you have this, side-by-side data, and then you could sort of build a simple model or apply a simple model to basically correct the data, to drive it closer towards high quality or research grade level. And this is typically done, there's a number of different approaches. People have used the simplest approaches, which is just linear regression. So I'll talk about how that works, but also I'll talk a little bit about some more complex methods that I think work a little bit better. And I forgot to mention that one good thing about each of these low-cost sensors is, I'll come to you in a second, is they also typically contain little modules that measure relative humidity and that measure temperature, in addition to particle mass that they estimate. So you're able to actually use that in your linear regression model or whatever model you're using. Yeah, question.
Yeah, so the question was saying, well, an expert in this space, but are you able to simulate conditions for detection, like in, let's say, African cities? Because I mean, the humidity and conditions are going to be different.
Yeah.
Than let's say New York. So
right.
Is it possible to simulate those conditions?
Well, that's a good question. I'm going to talk a lot about that. So a lot of the co-locations that we do should be local. Like if you're going to do one in New York, you shouldn't apply it to data in Africa. So that's actually the next slide. So yeah, it's co-locations, should be sort of environment specific to handle exactly that issue where you have, very different seasons and very different humidity and things like that. So this is a list of places where we're currently doing it. So there's, a few in the US, but then a lot in different major cities in Africa. So let's look at the, the correction or calibration models. Starting with kind of the simplest, So linear regression, very easy to understand and implement. It's been widely used in this space with decent success. As an example for PM sensors, you would, like I mentioned, you would take the the raw PM 2.5 signal that's coming out of these low-cost sensors. People also typically use temperature and relative humidity. Relative humidity is going to be the more important variable here. And so your linear regression, calibration model would be something like this. You just have your corrected PM 2.5, you have your regression coefficients here, your betas, and then the explanatory variables. So PurpleAir PM 2.5 refers to the low-cost raw data, temperature and humidity. And so that actually works pretty well. This is some data from Pittsburgh, Pennsylvania. The x-axis is the high-quality data. This is the reference monitor. The y-axis is the as-reported low-cost sensor. And you can see just right off the bat, there's some linearity here, but there's over-prediction especially at high humidity. So where my mouse is right now, you could see that there's some deviation here from the one-to-one line, so you have a bit of a bias. Applying this correction factor to the data, and of course, when you do this, you need to follow all the best practices of holding out some data as training data to build the model, and then saving data that that the model hasn't seen to validate the data. And you can even do people often do like a 5-fold model where they kind of hold out 5 different random 20% chunks and validate the model on against each of those. But doing that, applying this correction factor and applying it to the data that the model hasn't seen, you get sort of a much better agreement along this one-to-one line. So a much lower bias. The mean bias, the mean absolute error have improved quite a bit. So that works pretty well. However, a lot of these relationships between particles and humidity, or particles and or sort of the optics of how these things are detected are pretty nonlinear. We know that the way that aerosols interact with humidity is pretty nonlinear. So you might kind of wonder, okay, maybe we shouldn't use linear regression. So that people have proposed all kinds of different machine learning type approaches. Basically, if it exists in scikit-learn, it's been tried. So I've put a few of them up here. Tree-based methods, neural networks. Each of these are kind of good in their own rights. They do have some weaknesses. Particularly with the tree-based methods, you really don't get good performance when your data is outside of the range of the training data set. All right, so the tree-based methods, random forest, XGBoost can really only see only useful for data that are within that range. If you do have some data points that you want to apply that are outside of that range, then you're not going to get very good performance. So we're kind of seeking a new method, something that we would hope would perform better than a lot of these existing methods, and also overcome some of the shortcomings of a lot of these existing methods. And we found this method called Gaussian mixture regression. And so it's something that's, I don't think, very well known in sort of any field. It's been used in robotics and signal processing, and I think a couple of other fields. It's never been used, as far as we could tell, in air pollution, much less any environmental field. But we think it provides some pretty good useful methods here. And so what is a Gaussian mixture regression? Well, at its core, it's first of all, there's kind of like 2 parts. There's the Gaussian mixture model, which maybe people that have taken some statistics classes are probably familiar with Gaussian mixture models. But what they are is they sort of model the joint probability density of the input-output data as a number of Gaussians. And so it's sometimes thought of as a classification method, sort of like k-means clustering. But it classifies the data into a number of clusters, or model components, as we typically call them. And then it gives the probability that a given data point or a given observation is within some model component. And so this is different. This is, in my opinion, an advantage over something like k-means, because these are sort of what we call soft assignments. There's a probability that a given data point exists in each of the clusters that are identified. Whereas in k-means, as far as I understand it, it's sort of like it's either in that cluster or it's not. So that's the Gaussian mixture modeling part. What the regression does is it basically regresses the data against the distributions formed in each Gaussian mixture model cluster. And so what actually determines the regression, if you're trying to predict the output from the input, what you do is you sort of leverage that that probabilistic weight. So the probability the point belongs to a certain cluster is used as sort of the regression weight that goes in to to the prediction. So another, one advantage of this is that it can work well with missing data. So any subset of input and output data can be used for regression. This is sort of a schematic and also a little bit on the different equations of how it works. So first you have basically you essentially guess a Gaussian mixture model from a random sample of the data. So you initialize this Gaussian mixture model, you get your mean and your covariance, and then you sort of from there you assign the data points probabilities that they belong to each of these clusters that you identify in the Gaussian mixture model, and then you go back and take those probabilities the point belongs in a given cluster and use that to calculate an updated, basically Gaussian mixture model parameter set. All right, so the probabilistic weights, which are these HK values, are part of what determines the actual parameters of the model. And so you have an initial guess of the mixture model based on the random sample of the data. Go back, assign the weights, and then go back and calculate the updated mixture model, and then keep doing that over and over again until the values converge. All right, so that's basically step 1 and 2 combined. This is probably familiar if you're it's not, at a high level, it's not that much different than how like k-means clustering works. So this part is just sort of the Gaussian mixture model. Yeah.
I have a quick question.
Sure.
So practically, when you're writing your analysis, how many samples are you typically? What is that like as far as sample collection?
Yeah. So I mean, basically you have like a time series of data, a data set, and you can use it for we've tried it for as short as like 5 months worth of hourly data. So it's that I don't know exactly how many data points that is, but it's a lot. And we've also used it as long as like a year's worth of either hourly average data or daily average data. So yeah.
And then you've done this in places with lot higher micrograms per meter cube or whatever. Yeah. As opposed to the range you showed in Lamont.
Yeah, exactly. Yeah, that's
what's like the upper, like you go to 1,000.
Yeah, it can go up to like 1,000 micrograms per meter cube.
Still sort of that correction with humidity and temperature still relatively works.
Yeah. I'll show some results on that here in a minute. Yeah, okay. So the first 2 steps here, sort of the mixture model, and then the bottom step here is where you actually model the probability of the output data conditional to an input value as a mixture of Gaussians. And so you can see, basically here, the final predicted value, the expected value of the output data is going to be a function of the probabilities here, which are these H values, H sub K, where K is the number of clusters. So maybe this visualization, I often show this because it, I think, helps a little bit. So on the let me just sort of explain. On the top here, we have the model probabilities that a given data point belongs to a certain cluster. So this sort of purple corresponds to this purple cluster here. So this is just labeled cluster 1. And so obviously, when your input, so we have the input data on the x-axis and the output data on the y-axis. And so when your input data is, over here, obviously you have a high probability of being in the in that cluster. The parts on the far right are the probability density of a certain output value given a specific input value. All right. So if you have, an input value of, let's say, you have your raw PM data as your input value, and what you want to get is the corrected, the sort of predicted output value. This is what those distributions would look like. And so what it does is it sort of, I maybe missed this a little bit, but it takes a sort of a linear combination of all of the different clusters. And so that's sort of represented here by this pink distribution, sort of a linear combination of the sort of teal and purple one. And sort of takes that, the mean of that distribution as, the most likely value, and combines that with the probabilistic weights here, and then sort of gives you your final predicted value based, if you have some input value here. So if you were only going on one cluster, just predicted on, this cluster of data, then okay, you're given this input value, your final value would be somewhere here. If you were only going on the purple cluster, it would be up here. But if you're going sort of on the linear combination of both, then it's right here. So sort of just a visualization of how it works a little bit. Now to see what's the results of this. So we did this, yeah, question.
How do you think the number of clusters and what
Yeah.
that correspond to in the original model?
Yeah, that's a good question. So the number of clusters has to be identified ahead of time. All right. And usually, I mean, you can just trial and error it, but what we did in this paper was we used the AIC, BIC, so the Bayesian information criterion, and Akaike information criterion, I think that's how it's pronounced. And so we did that on the data and sort of found that in this case, 4 clusters was sort of the optimal approach. Yeah. So yeah, this is getting now into, let me just do a quick time check here. Okay. This is getting into the results. This is for 1 year of data collected in Accra, Ghana. So this instrument, this kind of white thing behind me is the high quality data, the reference monitor. And then I'm putting a low cost sensor on this little pole. And so we had this data collected for over a year, from March 2020. It's technically still there, but we sort of stopped taking the data around March 2021. And this is at the US Embassy, by the way. They have sort of this fancy data. So this teal color here is the US Embassy data. The purple is the raw low-cost sensor data. It comes from a PurpleAir. So you can see if you just compare that, there's some biases here. You see some high values. These are, I think, daily means. But you can see that, the purple is sort of over predicting for the most part the teal data set. And then we applied, several different models to sort of correct that. And so if you just look at the statistics for the raw model, if you're evaluating not the model, the raw data, it's not all that correlated, something like 0.5 R squared. It has a mean absolute error of 6.2. If you apply a multiple linear regression, you get pretty good improvement. You get 0.81 and 2.8. Random forest is kind of in a similar boat, but Gaussian mixture regression sort of outperforms both of them. And so, we sort of see that as good news. And, basically what this pink line is showing is the correct data applied. So now you can see that the pink line is almost right on top of the embassy data, which is this teal color. So essentially you're now getting some pretty good data out of these low cost sensors. Yeah.
Question, how consistent is the bias for your low cost sensors? I mean, if you have 5 of the PurpleAirs, would you be seeing some kind of
Yeah.
variability in how they're
So if they're sampling the same air, typically they are all pretty much identical. I mean, they correlate with each other close to, R squareds of 0.99. That's something that you have to test though. Like we usually turn them on, put them right next to each other for a little while and just make sure that that's the case. Sometimes you can get a bad batch, and then you would want to throw that one out. But yeah, we account for that.
Where's the embassy data for February? I cannot distinguish those colors.
I mean, it's like, I think it's sort of overlapping with the pink. Yeah.
So my question is, would it make sense to at least think about the possibility that the embassy data itself is wrong, and then you are like now forcing this poor algorithm to reproduce it, but it's not even correct.
I mean, it's certainly possible. All instruments have uncertainties and errors associated with them. I mean, the thing about this embassy data, this instrument that they use is it literally is the gold standard. I mean, it's what every US EPA monitor around the country uses. It's been very well characterized, very well tested. There's the Environmental Protection Agency has like protocols that are in place that say this is how you have to operate it. So it's certainly possible, but I think that it's very unlikely that the low cost sensor is giving better data than the reference monitor. Yeah. Yeah.
So how do you explain that spike?
Yeah, so it's kind of hard. We don't, without information about local sources of emissions, it's not easy to explain individual spikes. This time of year in West Africa, there is a huge amount of dust that comes from the Sahara. It's called the harmattan. And so I think that's part of it. There's also, there could be some, local sources. There's a lot of cooking with solid fuels that happens in Accra, with charcoal mostly. There's a lot of waste burning. There's a lot of vehicles that have that don't have sort of good fuel quality or good control technology devices. So there's a lot of sources. I mean, that's something that we're trying to think about more, is what are some of the sources? Yeah. So another thing that these Gaussian mixtures regressions can do is look at the different components over time, and it's able to kind of capture some seasonality in the different components, which I think is kind of neat. And so just going through here, or maybe I'll start at the top here. So you have basically the time that we collected data and then colored by the Gaussian mixture model components. There's two distinct wet seasons in Accra, Ghana. Basically when the ITCC passes going up and coming down. But you have an April-May wet season, and then sort of a September-October wet season. And that sort of comes up strongly in component 2 in the green here. You can see sort of most of April and May are component 2, and then September, October. The driest season of the year, and also the dusty harmattan that I was talking about, is November to February. And that shows up completely in component 4 for the most part. It can leak into March a little bit as well. So you see that, in this sort of yellow, or I guess, yeah, brown yellow color. In between the two rainy seasons, you have what's called a little dry season. So it's the ITCC is kind of, it's gone further north and up to, the Sahel. And so that's, sort of June to August, that's kind of in between these wet seasons. And you see that in component 1. And then the other component, component 3 is the one that really doesn't have that many data points. There's only 10 of them or so, but these are the extremely high polluted days, kind of those spikes that we saw. Those show up in component 3. Yeah.
I have a question about
do you have historical data to compare this one? I mean, obviously this is sensor.
Mhm.
Is there other plans to collect historical data to compare it and use this GMM or GMR on historical data that is, you know, maybe have a little bit more variability, or is there an expectation?
Yeah, I mean,
Or is that even feasible?
I mean, it would be nice for sure. The embassy monitor here has only existed since March 2020. So there's really not, you know, as I kind of showed at the beginning, there's hardly any data present, much less, you know, going back 5-10 years. So it's kind of difficult. I mean, what we do want to do with this though is take these corrections and apply them to like large networks of sensors so that you can get useful data, you know, in an entire city or an entire area. So that's sort of the application, which is what I'm going to talk about next. So I think in the interest of time, I'll skip this slide and go right to that point. And so what we did is we took this Gaussian mixture regression. I mean, you could do the same thing with the linear regression or the random forest. And we had deployed a network of 18 low-cost sensors, the same type of low-cost sensor throughout Accra, Ghana. And the locations are shown here. And basically, you know, these low-cost sensors just out by themselves without a correction factor, the data quality is suspect, and you know, you can't really use that data for action, for, you know, mitigation policy, for health studies, you know, the things that matter. You can't use just uncorrected low-cost sensor data. And so what we did is the motivation is sort of taking those correction factors and applying it, you know, to other data sets. And so that's what we did here across, you know, 18 different sites in Accra, Ghana. The dashed line here is the World Health Organization guideline. So this is sort of the healthy limit that the World Health Organization recommends. And pretty much all the sites in the city are quite a bit over that. And so these pie charts here, most of them are completely red, meaning that close to 100% of the days exceed the World Health Organization's daily guideline for healthy air. You can see there's a couple of them where maybe this one's only 69%. But, you know, moral of the story is that the air quality is fairly impacted in Accra. We did something similar in Togo. I'm just going to go through a bunch of different places where we've done this. We had much fewer sites here in Lomé, Togo, which is very close to Accra, Ghana, still in West Africa. This is sort of doing the co-location that I mentioned. This is the professor at University of Lomé. Similar story there. Actually, the pollution levels were a little bit lower in Lomé than in Accra. I think that's just due to the fact that there's less cars, there's less people in general in Lomé versus Accra. Accra has like a couple million people, and Lomé has maybe just 1 million people. So it's maybe twice as big. Let's skip this in the interest of time and go on to Kinshasa in the DR Congo. So this is really interesting because Kinshasa is an enormous city, and it's basically completely forgotten amongst the global community. Kinshasa has a population of about 14 million. So it's just absolutely huge, and it's growing fast. And I think by 2050 or 2100, it might be one of the largest cities, or the largest city in the world at this, under this current population growth. It's right across the Congo River from another city called Brazzaville. And this is also a different country, by the way. So this is the Republic of Congo, and then the Democratic Republic of Congo. So we deployed and calibrated a small network of low-cost sensors, just kind of the similar way here that I mentioned. We hadn't developed the Gaussian mixture model yet. We hadn't heard of it at this point. This was in like 2019, 2018. So in this case, we only used multiple linear regression, and we also kind of just threw in random forest as well, just for comparison. but the data works pretty, the comparison here was very good actually with the low cost sensor. Sorry, yeah.
Something, so when you deploy, let's say in Lomé
Yeah.
or in Kinshasa,
Mhm.
you also have the high quality reference model.
Yeah. Yeah. So in the case of Kinshasa and Accra, there's one at the US Embassy, but they're all like very new. In the case of Lomé, we installed one ourselves that, I just purchased. And that's what's in this photo here. So that's a key, limitation, is that you kind of need, and I'm going to actually speak to that here in a minute. But the multiple linear regression actually works pretty well. So the data was much better correlated just out of the box compared to what it was in Accra. But it was much more biased as well. The mean absolute error was about 15. And so we were able to get that down to about 3.4. The correlation improved a little as well, but it was already pretty good to begin with. And then, applying this to the data, we saw very high levels of pollution. The five site median daily PM2.5, was something like 42 micrograms per meter cubed. Just as a reference, the World Health Organization guideline is 15. Or no, sorry, for daily. Yeah, for daily it's 15. So quite a bit higher than that. We saw, each of these this distribution of these violin plots are basically distributions of daily mean PM2.5. So we were seeing daily means, up to about 150 micrograms per meter cubed. So that means, at any given hour, the concentrations could have been much, much, much higher than that. And they were. If you look at the hourly data, there were definitely spikes that got up to 500 or 1,000, which is pushing the limitations of the instruments to really even detect at that level. And I'll kind of switch gears now. But this is just some photos of some of the work we've done. We're working on this in many other cities. I mentioned capacity building. So this picture here in the middle is me working with the Environmental Protection Agency of Ghana, training them on basically how to do a lot of what I just presented, how to work with low cost sensor data and how to analyze it. And yeah, how much time do I have left? Because I know there's been some questions and stuff. Okay. Okay. Can I just go to my summary? Okay. So maybe I'll skip ahead here. And probably the last point. I'm not going to get through my whole talk, unfortunately, but that's fine. I'm happy to share the slides. This is getting to some questions that I think came up in the real time in the talk. It's, how can we scale this up globally? So I mentioned, you have this sort of local co-location everywhere, and that's really a good method of doing it, and it's accurate, but there's a practicality issue because you're not going to be able to get one of these, fancy instruments everywhere in the world, and you're not going to be able to get them at the quantity that, for example, low-cost sensors exist. So if you go to PurpleAir's website, there's, I don't know, tens of thousands of low-cost sensors around the world. Even in the US, we have a pretty good density of these reference monitors in the US, but even the US has many areas that are underserved by those monitors. So a cool thing to do would be to say, is there any way we can just do some correction factors without having to have these local co-locations? Because it isn't going to be feasible everywhere, I don't think. So that's sort of the question that I'm getting at. And this is part of actually a DSI seed funding project. So thank you to the Data Science Institute. But this is what we're calling it as sort of a universally applicable Gaussian mixture regression for correction of low-cost sensors. And universally applicable in quotes, because it may end up being more of regionally applicable, or US versus West Africa, versus places like that. But sort of an ambitious goal of doing that. And so what we're, this is very much ongoing. I don't really have any results right now. One of my students is going to be working on this over the next 2 or 3 years. But our goal is to basically have different components in the Gaussian mixture model for different pollutant mixes and for different climatic regimes that can span a wide enough range of input data and thus be applicable to many different regions and many different cities. And so what we're thinking of doing is basically taking these local co-location data sets across maybe 5 or 10 diverse locations, meaning like spanning the entire parameter space of air pollution, of temperature, relative humidity, and sort of putting that all into one big Gaussian mixture model, and then sort of applying that into other cities. And if the data sort of cover, if the sort of model training data cover, the input data of a given city that we want to apply it to, we think it should work. Now we'd have to test it, and so we would evaluate the model on at least 20 independent co-location data sets that the Gaussian mixture regression hasn't seen. And we already have sort of this data set at our hands, just through work that my group has done. We already have at least probably 50 different co-locations around the world. We have some in Delhi, India, maybe one of the most polluted cities in the world in terms of particulate matter. We have several in Africa. We have several in the US that kind of give you this nice range of different levels and different conditions. But we can also use things like the PurpleAir database, which is all publicly available data. OpenAQ, which is a company that compiles a lot of publicly available data, both from low-cost sensors and from reference monitors. So we can also use that and throw that into our model as well. So that's sort of the next steps. That's the bigger picture. I think maybe should I just go to my summary now, Alexis? Yeah, and wrap up. Okay. Okay, maybe I'll keep going just real quick. And the next thing I was going to talk about is sort of completely different. But instead of statistical, yeah, sure. Sure.
Can I ask now?
Yeah, sure.
So going back,
Uh-huh.
I collect a lot of field data with low-cost sensors, with motorcycles.
Mm-hmm.
Is the diversity of location, and I do primarily rural, but do get to the edge of the cities quite a bit. Rural is maybe not as much vehicular.
Yeah, it's
But
like
that's one. And the second question there was, what I read in the literature, and a decade ago, we did a lot of measurements indoors, and Batkinney was here, and those were like in thousands.
yeah.
Now, if the health implications are because you are close to something high, maybe bad, as opposed to general air being 50, let's say, micrograms per meter cube, as opposed to 2000. To what extent is, like in rural settings, it's almost entirely biomass burning, right? Is there value to moving the reference sensor for an hour, a day at a time, along with the low-cost sensors to locations where the sources are proximate?
Yeah.
And you get this diverse geography, but you sacrifice the fact that you're going to have that sensor in one spot for a year.
Yeah.
I wanted to get your thoughts on that.
No, I think that's a really good point. We've actually been trying to address that a little bit, because most of all of these data sets that I'm talking about are in pretty urban areas, major cities. But as of this year, actually, we've put some reference monitors in rural areas of Ghana, sort of away from the big cities. And so I do plan to incorporate that into these models, because I think that you do need to have, you have to have the lower concentrations represented as well. You have to have the different types of sources represented as well. In rural areas, the main pollution is from just cooking, and it's usually like done with just wood, at least in many parts of Africa. In the rural areas, it's, people can try to implement, cleaner fuels, but at the end of the day, it's free to just go chop down a tree and use that to cook your food. So yeah, I think that we would.
Do you think geographic diversity would actually be valuable?
Yeah.
Even though at each location you're not getting a year worth.
Yeah, I mean, a year worth of data is I would say pretty ambitious. Other people, in the literature would say like you don't really need a year. There's a question of practicality as well. It's like, yeah, do you have a year just to train your model, or do you want to get some results quicker? So I don't think it necessarily needs to be that long. You could definitely move it around in shorter periods. Yeah, it's, it would be nice to have like a good representation of the different seasons, but.
And the other quick question, if you don't mind, is that you showed that Gaussian mixture results.
Yeah.
That there were 4 different components, in different times.
Yeah, this one.
And so yeah, this one. My question was, when you identify that there's a dominant component, is the model for that component different, or you're just identifying the component, but the correction is the same based on all?
Yeah, so it's the latter. The correction is the same. It's some mixture of each of these components, but what this is showing is just like, what's the dominant component right, the highest probability of each. Yeah.
At a particular time.
Right. Mm-hmm. Yep. Okay. Yeah, so we're already past 12, so maybe I'll just wrap up. Let me just go to my summary slide, and then I'll take more questions if there are any. Let's see here. Yeah, so just to wrap up, air pollution data is sparse globally. I didn't actually get to talk about the climate stuff, but that's okay. I'd rather have this, back and forth discussion. I talked a lot about how low-cost sensors can help, in resource limited areas, but it's vital to calibrate them. You can't really use them just out of the box. You can get, misleading data, bad data. So we talked about, about that a lot. Well-calibrated air sensors can have, many useful scientific purposes. I didn't get to talk about this too much either, but, besides just having this data and characterizing the air quality, you can also use this data for all kinds of different applications, like health studies, which is something we're trying to do, for air quality models. So not statistical models, but physical models that determine or that model the emissions and the chemistry and the transport in the air. Those always need to be evaluated by real world data. And so having, these well-calibrated air sensors can really do that. Yeah, there's other aspects as well. Yeah, and so I think I'll probably just stop there. And if there's any more questions from the people on Zoom or here, I'm happy to take them. Thanks. Yeah.
Yeah, it's a little bit related to DJ's question, but even when you're doing this co-located experiment, you have a low-cost sensor and you're trying to effectively to the high-cost reference sensor. To what extent does the sighting of this co-located setup impact? I mean, I'm talking about the airflow, turbulent flow. Like you showed you had it set up on the side of the building at Lamont.
Yeah.
If I put it in the middle of the field, is the relationship still the same? If I put it on the other side of the building, there's going to be sort of trends in airflow, and or if I put it on the corner of the building, does that change
Yeah,
how the air is effectively ingested into the sensor?
absolutely. Yeah. I mean, the best practice is to not put the sensors like on a corner of a building or, against a big face of a wall, because then kind of, as you said, there's turbulence can do some weird things, and it could be a lot different than having it sort of open. So the best practice is to try to have, sort of 360 degrees of open air around your data. And I mean, that's what we strive to do in most cases. The picture at Lamont was sort of just that was just more of a training exercise that I was running for students. But yeah, it's definitely important consideration. And you see often a lot of people that maybe are just putting these like against a window or something, and that sort of does introduce another layer of complexity that isn't really talked about a whole lot, in the literature. It's sort of, I don't think we're really at that stage yet. People are still grappling with earlier issues than sort of that. But yeah, it's an interesting point. Sure.
How often do LCS need calibration treatment?
Yeah, that's a good question, and it's there's not, I don't know that there's a hard and fast answer for all applications, but I think the important thing is to span the range of conditions, and that this includes not just sort of the meteorological conditions, but also the sources. So like in certain times a year, you have different sources of pollution, especially where you have 4 seasons. So if that requires doing an entire year, then maybe that's the answer. Some other alternatives might be to kind of do short-term calibration periods, but kind of like sort of intermittently. So bring the sensor, co-locate it for a few weeks in the summer, then go deploy it, have it get regular data, bring it back in the fall, co-locate it, go deploy it, bring it back in the winter, just for like short periods of time to take that. I've seen that strategy used as well. But people often point to the seasonally, I see in the questions, says seasonally, people often point to that as a good metric, because that kind of determines the sources and the environmental conditions. Yeah.
I really like that you have a picture of the particle in the chamber with the water coating around it.
Uh-huh.
So I was wondering, alternatively, or maybe in addition to the statistical correction that you described, would there also be a chance for just understanding the pure physics of the process and doing the correction out?
Yeah, that's a really good point. Let me just pull up that figure real quick. There is a active part of this space that prefers that approach, that they measure sort of like the hygroscopicity, as we call it. It's sort of the water affinity of these particles to take up water, and use that as a correction factor. And so it's entirely physics based and not statistical based. So that's a viable option. People are using it. It can be difficult getting that hygroscopicity data, that water affinity data, is a very expensive measurement. So it's not always practical in sub-Saharan Africa. And so we sometimes have to revert to these like empirical statistical methods, but absolutely, that's might even be a preferred way of doing it, honestly, is to do the physical based approach in a perfect world.
Or a combination, right? That you first do the
Yep.
some kind of physical clean,
Mm-hmm.
that you present the algorithm with something
Yep.
a little less chaotic.
Yep. And people have started to do that a little as well, combination of both. Yeah.
Can a small solar panel be a low cost?
Yeah, I mean,
we have millions of those in Africa.
Well, I mean, yeah, the solar panels, the instruments that have solar panels on them are a little pricier typically.
Look, I mean, can the solar output, which is affected by the integral of the whole light situation.
Oh, from like
And,
photo. Okay.
So people, by the way, are noticing that in the field that, so they see two big impacts on solar output. One is due to cloud cover
Yeah, and
and one
particles.
is due to fire.
Yeah.
But the cloud cover bit, they're able to model because of remote sensing. There's a lot of ways to measure.
Mm-hmm.
They're not able to figure out the effect which is closer to the sensor. Levels of dust,
Yeah.
I don't know, fog, smog, I have no idea what impact it, but it is pretty significant. So
Yeah. So from like a solar energy perspective, I see what you're saying. I mean, it sounds feasible. I mean, it's I think sort of there would be a lot that needs to be figured out on that, but I mean, it sounds fairly promising.
we'll chat later.
Yeah. Uh-huh.
Yeah.
Okay. Thanks, everybody.
Okay, thank you.